All right. Welcome, y'all. I'm seeing some familiar faces, which is great. If this is your first time with us, welcome. My name is Anna Holder. I am the program coordinator for our word salad coming in hot. Hold on, y'all, for this early in the morning. For California's surface water ambient monitoring program, and specifically our bioaccumulation monitoring program. This is our penultimate 5 out of 6 series course of this series. I am joined today with the Safety Work Group co-chair and our lead scientist, Jay Davis, if you want to give a wave. And he and Michael Weaver will be taking on the majority of today's content, but I'm going to kick us off. So I'm going to talk a little bit more about the swamp data dashboard. We've talked about this a little bit in, I think, the first training earlier this year, but we're going to do a demonstration, and there's slides with some, after the fact, if you want to remember what that button does, there's content there. It's going to be short and sweet, but we'll have time for questions and discussion as we go along. The bulk of the training today is talking about how do we analyze and interpret the data that we collect through our swamp bioaccumulation monitoring program? And Jay's going to take us through that content. I've seen the slides. We're going to take a break to give the minds a rest, and then we'll come back for questions and discussion if you have any. And then Michael is going to talk to us about there's some scripts that he's developing that we'll be sharing through a GitHub repository. If none of that makes sense to you, that's totally fine, but a lot of folks might have staff or you yourselves use programming languages, specifically R is what we'll be talking about. And these scripts will help you basically recreate figures and things like that Jay will have gone over, and Michael's going to walk you through how to do that. We'll go through some questions. Yeah, Jay?
Yeah, maybe while we're on this slide, I think it'd be good to encourage people to ask questions at any time. Do you agree with that? So feel free to interrupt us at any time. If you've got a question, you don't have to wait until the question session.
Yeah, the schedule is very flexible. So if we get in discussion in the middle, that's great. Jay and I will both be, when we're not presenting, we'll be monitoring the chat, but feel free to use the raise hand feature or just unmute yourself and speak up. All of that is welcome. And then I'll talk a little bit about a few next steps, and we'll close for the day, and we'll close on time. We're gonna start. It's early, so I want to get our juices flowing with a poll. We're going to have 2 polls today. Basically, what's going to happen is I'm going to launch the poll. It's going to be clumsy because I'm sharing screen, but I'm going to do it. I'm going to launch the poll. A box will pop up on your screen with the question. The questions will also be on the slide. So if you want to see it in more than one place, you'll be able to. Once you press submit, the box is going to disappear from your screen. When we get enough folks that have participated, I'll share the results, and we'll talk through them together and talk about what we're seeing. So hold on to your hats. Here we go. Let me launch the first poll. So it should, the box should be on your screen somewhere. We've been talking a lot about different phases of monitoring and different things that we consider as our statewide program. And we're just checking in and seeing where you're at with that process, if at all. So where are you with your monitoring? Maybe you're thinking about monitoring. That's why you're taking these courses and checking us out. But you aren't planning anything yet. You're just kind of window shopping when it comes to monitoring. Maybe you're actively planning. You're writing your monitoring plans or your quality assurance plans. Maybe you finished that and you're actively monitoring. You've got teams in the field today or in the last couple of weeks or months. Maybe you finished your field work and you're sending your tissues or what your samples to labs for analysis. Or maybe you've gotten that data back and you're doing your quality assurance steps, seeing, making sure the labs analyze the data in a way that meets your quality standards. Or maybe you're here today because you've got that data and you're thinking about how you want to analyze it. And that's what we're going to be talking about today. Or maybe you're not interested in monitoring at all. You're just checking us out. Maybe you want to use the data that Swamp has publicly available and you want to think about how you want to do that, or something completely different. Um, so hopefully I've stalled enough and people have been able to complete the poll. It looks like we've got 71%, 10 out of 14 folks. I think Jay and you might not be counted, which is okay.
Yeah, I didn't vote.
Okay, great. Let's see if we get, maybe if one more person presses submit. Okay, great. We've got 11 out of 13 folks, and a couple folks have just joined as the poll was happening, so they might have unfortunately missed it. So let's see, we're going to end the poll and I'm going to share the results. Can y'all see the results on your screen? It doesn't show up in the recording, so I'm going to just talk through the results together. And so first, we've got about a little over 30% of folks are thinking about monitoring, but not actively planning. We've got a person that's planning, 2 that are in the field. Their folks are collecting data, potentially as we speak. We've got another couple of folks that are analyzing and interpreting data from recent monitoring, which is great. And a couple of other folks that said other, something else not on the list.
So Anna, at some point, when there's time, if and when there's time, I would like to hear what the current monitoring, like the scope of the monitoring that folks have going. I assume it's probably small scale compared to what we do statewide, but it'd be good to have an idea of what they're actually doing and might influence how I present things.
Yeah, I think we've got some time for that. For folks that were responded with they're actively monitoring or you're analyzing data that you've already collected or even other, is that something that you'd want to share with the group? What are you monitoring for, maybe? Or how you're thinking about analyzing your data, anything like that is welcome. No wrong answers here. Or maybe you're thinking about monitoring or you're planning for monitoring. Like, what are you thinking about? What do you want to monitor
Yeah.
for?
How many samples are you planning on collecting? How many locations? That kind of stuff.
Habs and E. coli totally counts, Sarah. Yes. Good morning. We've talked a lot about Habs throughout this course, even though we're focused on bioaccumulation, but Habs and bioaccumulation are interacting.
Yep.
Okay. All right. Well, if you, nice. Sarah's got a monitoring program for Habs and coliforms and E. coli throughout the basin. Fantastic. Great. Well, if folks want to share anything else in the chat, feel free or chime in at any time.
Yep. Thanks.
Just want to make sure, can y'all still see my screen? The little
Yes.
Okay, great. So as I mentioned, we've done a bunch of other trainings, 4 other trainings. We're going to touch on some topics that Jay talked about, specifically study design, during our February training. And so you'll get the slides later today, my hope, or early tomorrow. And there's links and everything in these slides. So you'll be able to access those links at your leisure if you'd like. So the Swamp Data Dashboard, we're going to talk about it a little bit today. It's an
Hey,
interactive.
Anna,
Yep,
sorry, before you jump in, I want to sort of give a plug for the importance of this with regard to reporting and interpretation.
sure.
Uh, One of the key things that anybody will be doing if they're collecting data anywhere in California is, getting your data, and then maybe even when you're in the design phase, you want to look at the water body that you're planning to monitor or the water bodies that are in the neighborhood to see what kind of data have been generated prior to the work that you're doing. And then when you get your data, you compare your data to the past data from either your water body or other nearby water bodies. So understanding how to access data through the dashboard is really crucial to doing your data interpretation. So a little bit of a plug, and I'll also mention the dashboard again when I do my presentation.
Awesome. Thanks, Jay. There's a couple of different places where you can access the raw data that comes from our program. One of them is CEDEN. That's where Jay and Michael pull the data from for the analysis that they're going to talk about in a little bit. You can also get it from the California Open Data Portal. The cool thing about the Swamp Data Dashboard is it has a nice user interface. CEDEN, as we all know, um, challenges our patience at times, to say the least. It's really difficult to work with. It can be. And so the Swamp Data Dashboard makes it easy to find what you're looking for. We've got, it has data for all swamp programs. So not just bioaccumulation, but our harmful algal bloom program, bioassessment. So if you're interested in stream health, looking at bugs and algae, all of that's in there as well. It goes from year 2000 to present. The other data sources have data before that. You can download and filter data. You can check out graphs. And we're continuing to review and revise the Swamp Data Dashboard, adding more data types, adding more functionality and features over time. So this will continue to be a living resource for everyone as we move forward. And there's a link to the bottom of it here. And I'm going to do a demo in a little bit. But before we do that, the way I use the dashboard, I go straight to the filters. So you'll notice on the left-hand side here, there's a bunch of like a gray area with filters. I don't even look at, at the map when I start. I go straight to the filters because there's a lot of data in there and I want to get to what I'm looking for. The way I filter data is by program because I'm always thinking about bioaccumulation. That filters a lot of the data out. So I'll start by selecting the program that I'm interested in. You can skip that if you want. You can filter by region, waterboard region, or by analyte type or species. So you can have like tissue, or I'm looking at organics data. We're going to talk about tissue because we collect fish and shellfish tissue for bioaccumulation. Or if you're just looking at HAPs, for example, and you want to see all of the cyanotoxin data, you can skip all of the other things and go straight to the analyte. The cool thing here is it's a drop down, but there's a lot of options. So scrolling all the way to M makes my finger hurt. So you could just start typing mercury or cyano or something, and then the analytes with that match that spelling will pop up and it'll make your search a little bit easier. If you've selected all the filters you want, you can press apply filters and the map will change to reflect that. Or maybe you filter too much and you want to start from the beginning, you can clear your filters, or you can just zoom in and see what you got. Once you've selected your filters, you can kind of switch your gaze to the map. And there's some features that I wanted to point out at the top of the map that are super handy. We're going to talk about the data download a little bit later, but I guess starting from the bottom left, if you have filters or you're zoomed in or whatever, and you want to kind of go back to the beginning, you can press this little house button and it'll resume to the default map extent. So you'll be able to see all of California. Base maps are basically what it looks like behind the points, and you can have like satellite imagery. It's all accessible through the application, Streets View, something like that. I think it's like, I don't know what the standard is, but you can, if you want to switch to satellite imagery, for example, that's something that I do quite regularly just to see what what it looks like. That's where you do that. You can zoom in and out using your mouse wheel. One functionality that I'm gonna try and get in there is being able to like drag your mouse over the screen. That doesn't work just yet, but you can zoom in and out using your mouse wheel or the plus and minus buttons here. You'll be able to toggle between the map and the table. So the map shows you the points. If you want to see things in a tabular format, you can click the table, and the points that you see on the map will also be shown in the table. You can go back and forth. The different layers of the map will be shown. The swamp station, so that's the data. That's what we're looking for. Most of the bioaccumulation data will be blue points. We have reference sites in our bioassessment program, and some of those sites are they're represented in those orange triangles. Some of those sites are also bioaccumulation sites. So you might see a triangle like you do on the map here. That's all that means. For bioaccumulation contexts, it's the same as the blue points. There's also integrated report layers and things like that that you can turn on and off. We're mostly focused on the point data, so that's the only thing we'll have on. If you're looking at the table, you'll notice this button up here then turns to the map, so that's how you toggle back and forth. And it shows you oh, I wanted to go back. Right, this here. The number of stations is how many points are shown on the map. So as you filter and zoom in, it might go from 520 to 12 or 3 or whatever. So that'll show you just numerically. Sometimes it's helpful to see, oh, I'm looking at all of the bioaccumulation data in all of California or region 5, and this is how many stations are there. And that's super handy for me. You can, this button over here, you can filter the table by the map extent. So if you're zooming in and you only want the table to show those points, then you can click that little filter button. And then this is really super helpful. Everything's collapsed when you first look at the table because the tables can get really big if you're looking at 520 locations, right? If I'm only interested in one location, you can select that, press the select button close to that station, and it'll show that data in a graph. Similar to clicking a point on one of them on the map, and it'll kind of show you the station page for that station. You can click this arrow here and it'll show you the data in tabular format. So for Lake Mendocino in this case, and you can, if you've done that a couple of times and you want to kind of collapse everything or expand everything at once, you can use these buttons at the top to walk through that. If you expand for one station, this is what you're going to be looking at. So you've got the station code. That really matters for our database, the station name, the type of analyte that you're looking at. I filtered by mercury, and you can only really look one analyte at a time. So that's one thing to note, but you'll get your analyte, the species that we're talking about, the year the data was collected, the result, so what was the mercury concentration, and the result type. So the cool thing about the swamp data dashboard is, let's say we collect multiple largemouth bass at a lake in California at one location in 1 year. We already average the individuals in a way that is consistent with how Jay will talk about analysis later on. So that's one step that you don't have to do. It's already done for you. And if you want the raw data, we can show you how to find that.
Anna, before you go on, I want to, thanks for mentioning how we, the different ways of treating mercury, and just I want to flag that for future reference. I'm going to talk more about it later, but there are several ways that we present mercury data. Sometimes it's just an average of composite samples. Sometimes it's a simple average of individual samples if we analyze fish as individuals. The most powerful and elaborate thing we do is estimate an average of a length adjusted average for a standard size of 350 millimeters, and I'm going to explain that. And then sometimes when we can't get a good regression between length and mercury, then we just do an average of bass that are of legal size. So for mercury, there's several different twists of how we present the data, and it's just important to, when you are interpreting your mercury data, to make sure you're comparing apples and apples in terms of the statistics that are being used. So when you're pulling data from through the dashboard, make sure that you're paying attention to that result type when you're doing your mercury comparisons.
Yeah. The other nice thing is these averages are done for when appropriate for all analytes. So something that we've done in the past is we've actually gone straight to the swamp data dashboard because we want to pull data from our database. It's already averaged for us so that it's like much easier to go straight to a mapping application on our end, for example. So we would search the analytes that we were interested in. So we wanted mercury and we wanted PCBs. And so we just did the filters the same way each time and downloaded the data. So you can see this button here. And it's structured in the same way. So it's easy to combine the data once you get it out of the application. So if you look at Clear Lake, I clicked on the data point, and this screen popped up on the left, basically showing all of the mercury data from tissue samples over time. You can toggle between a graph and a table. And then on the bottom, you can see that there's the colors of the points represent different species, and that key is down at the bottom. You can also add, here's what it looks like in the tabular view, similar to what we mentioned before, but just for the data that's shown on the screen. If I want to compare data from multiple locations that are close together, for example, you can click the Add Station button and then click on the points that are of interest, and they will pop up for the comparison. The stations will be different shapes, and the species, the fish, will still be different colors. And you can see what that looks like in the graph below. And if you click on this download button, you can download just the data that's being shown in the graph. So a couple of different stations that you're interested in, the analyte that you're interested in, and it's a much smaller and easier way to download data if you're looking for something very specific. And you can change what you're filtering here. So maybe you have your map extent the way you like. So you're seeing the locations that you're interested in, but you want to see the difference between mercury and PCBs. You can change what you're viewing up here and without having to change your map extent. You've played around in the Swamp Data dashboard, and you are ready to download data that is of interest to you. You hit the download data button at the top, and it takes a couple of steps. So one cool thing is if you're interested in just getting the station information, where the points are, you have a Get Stations data button. So you're not going to be downloading the data associated with those stations, just the station information. And I'll show you what that looks like in a table for a second. So that's helpful, particularly if you're submitting data to SWAMP, because then you have the station information in a way that the database requires. That might not apply to you. That's fine, but that's a tool that we've had requested for the dashboard. You can also get the results, which is why we're here, right? And you have to get the results data to download data. As I mentioned, you can only download data for one analyte at a time. So that's a little bit clunky, maybe going through the CEDEN query tool that'll be talked about a little bit later. Maybe that'll make more sense for you, but for simple analysis, this is great. The process takes a couple of clicks. So you're going to get the data first, and that's basically going to tell our systems, okay, package that data for this person. Once it's ready to go, you're going to hit the download button, same buttons, but they're going to go from gray get buttons to blue download buttons. So you're going to click that, and then CSVs will pop up in your downloads file, wherever that is in your browser. And you can go to your downloads and the data will be there for you. And you can close the download data view. Once you open up those files, this is what it looks like. So if you're just looking at stations, you've got the station code name, the lat long, which water board region that station is in, and the region name. And that's it. It's a short, small file with only station information. But that's not why we're here. We want to look at the results, right? So this is a much larger file. There's many more columns in it because we're sharing more information. The first chunk of it, A through F, is this same station information and project information. The project information, if you're interested in looking at like the 2010 data, for example, that we collected, you'll be able to sort by project if that's of interest to you. It's not of interest to most people, but that's what that's for. The middle chunk here is what you press download for. That's the species, the data by species, by location, analyte. You can see the different result types that we talked about before. So it's an average of individuals or average adjusted length, average. The year, you'll notice there's a target latitude and target longitude. So for anyone that's gone out sampling, you make a plan and then you get out in the field and the plan changes. You might not be able to go exactly where you planned, or you have to adjust a little bit. So that's why it's called the target. And then the far right of the data set shows data quality notes. So things that you might want to check out. You'll see that most of the data passed all of our data, the SWAMP data quality checks, but maybe there are a couple of points where some review is needed, and there's the specific quality code there that I can show you. I'll provide a link on where to find, like, how to interpret what that means. And it also shows you the number of individuals in the average. So for the black rockfish in row number 2, the result of 0.251 micrograms per gram wet weight in 2010, that is a compilation of 10 fish in the average. So you can see that varies. Okay, I'm going to do a demo, and hopefully that answers a number of questions. But feel free to chime in at any point. So when you first open the Swamp Data dashboard, this is actually a really helpful window that most people just go straight to the dashboard and don't look at it. But if you're interested in learning more about the data There's information about where we get the data. So there's links to the open data portal, a document that provides the data quality categories. There's a link to it right there. Instructions on how to download. And if you're interested in like the backend application, it's all on GitHub if that's of interest to you. Anyway, you can go to the dashboard. It also tells you when the dashboard was last updated. I think it was like a couple of weeks ago. So here's all of the swamp data available in the dashboard. And just like we talked about before, I don't got time to look at all that. So I go straight to bioaccumulation. And I might apply the filters as I go. So I'll apply the filters and you'll notice it went from over 6,000 stations to 560 just for bioaccumulation. But maybe I only want to, I don't want to filter by region. I just want to zoom in a little bit. And I want to see so I was just typing in mercury. You can see the different types of categories. So we've got sediment data or water data. I'm going to go with the total mercury in tissue. And I'm going to apply the filters again. And it went down to 520, but that's for all of California. So I'm going to click this little filter button and it'll filter to what I'm zoomed into. That's the current extent. And then we go down to 254 stations. But maybe, so I'm using my mouse to zoom in and out. So here's Clear Lake again. And maybe I want to know more about this lake over here. So I'm going to click on that, Lake Mendocino. So I can click on that button and the graph is going to pop up. You can see my species down here. And I want to check out this point because it's close. And this point. So we've got Lake Mendocino, Russian River, and Cold Creek at Potter Valley. And if I wanted to download just the graph, then it goes straight to the CSV, so I don't have to do the double download. I can look at things in the tabular format. And maybe for these 6 stations, I want to download the data. So I'm going to go straight to the get results data. And then I'm going to download the results. And you can see that it popped up again. If you're downloading data for more stations, all of California, it's going to take a little bit more time, but it goes relatively quickly. I got my CSVs, so I'm going to close this. And I'll open the CSV. And this is what it looks like. Okay. And that's how I use the swamp data dashboard. Others might use it differently. But I see Sherry has a note in the chat. The comparison feature is helpful to see where safer fishing locations might be. Good to know where the toxins are and also where the fish are alternatively. So compare largemouth bass to see fish that gather toxins and then fish for lower mercury like trout, for example. Was there anything else you wanted to add there, Sherry?
No, it didn't gather the whole thing I said. It was just good to know where the safer fish are alternatively.
Mm,
So, because we're
awesome.
usually looking for where are the toxins, but for a lot of the tribal communities, we're trying to figure out where we can fish. So,
Right. That's safe. Are there any other questions about how to use the swamp data dashboard that's coming up for folks? It took me a couple of kind of tries before I began feeling comfortable with finding what I need really quickly. So that's why we have these slides will be available so you can walk through step by step again if at a later time. Okay, I'm going to stop sharing.
Before we kind of jump away from this topic. There's a detail that I want to highlight. When you were selecting the analyte for fish, we measured total mercury, even though what we're really concerned about in water and in general is really methyl mercury, but 95% of the mercury in fish is methyl mercury. So, and it's cheaper to measure total mercury. So it's a standard practice to measure total mercury, but that's really telling you how much methyl mercury is in the fish. The methyl mercury is what's really posing the risk to people that eat the fish. So an important detail on mercury.
And that brought something else up for me, Jay. So as you apply the filters, your options in the filters will change. So if I clear all of my filters and go back to the beginning with our 6,731 stations of swamp data, if I choose tissue and apply that filter, oh, I might have to do, let's do San Francisco Bay. It's going to zoom in. And you'll notice that I still have a lot of analyte options, but the program is limited. So only the bioaccumulation program collects tissue data. So you can collect tissue or bioaccumulation. There's less scrolling if you go by program. Just ask me how I know. So you can apply those filters. And if you want to do, there's a lot of PCBs options, which is frustrating and something I'm going to try and get in just a PCB option that combines everything in a way that's appropriate. But let's say you want this one and you can apply the filters again. And then it shows you've only got 5 stations with PCB data. But if I look at mercury, total mercury, as Jay said, and apply those filters, I've got 53 stations. So we have lots of mercury data, fewer organics data available. Okay.
I have a couple of a question or comment or two. This is pulling data from CEDEN. I'm wondering why RMP doesn't show up, or like data. Is that, oh, you picked the bioaccumulation program. So would the RMP data show up?
It's only showing swamp data. So only data from swamp sources at this
I
time.
see. Yeah.
Adding in other data sources is something that we're thinking about, but it makes things more complicated, and
Yeah.
it slows down the dashboard, but it is something we're working out. So hopefully in the future.
So if it's not there, a question for those that are trying to do a deep dive on their specific water bodies, where can we get the RMP data? Perhaps we could share that out either afterwards or in a link.
Yeah.
Yeah, sure. Yeah, the RMP's got a data access website. So we got our CD3, we call it, contaminant data display and download. So we can definitely send the link out for that. And that's, there aren't that many major programs, but that is another one of the major programs generating data in California.
And at the end of the slide deck, I'll add a link to the RMP data download spot. Great question, Sherry.
Great, thank you.
Another thing to note, and I know Sherry's been tracking bioaccumulation data from swamp for a long time and remembers the Safe to Eat portal. Anna, can you explain the status of that? This is kind of the next generation of data access through swamp.
Yeah, so we talked about, I think in the first training, that the comparison between the safety portal and the swamp data dashboard. So that's a longer explanation is in that training. But basically the safety portal, we stopped adding data to that portal in 2017. I think it only goes to 2017 data. And the swamp data dashboard has all data that's available from 2000 to present. So as we get data in from our 2023 monitoring, for example, once we do our quality checks and it's pushed to CEDEN, it goes directly to the Swamp Data dashboard. So, but it doesn't get pushed to the Safety portal anymore. So this is definitely the next generation. If there are features of the Safety portal that you like, click around this and you're like, wow, Safety portal did this way better. Let me know, and we can work on adding those features back in. We're tackling it as we can.
My
yeah.
favorite feature of that was to be able to sort it by the fish tissue safety levels that are used by OEHA. I loved that. And then to be able to sort, then after you've done that, to sort by, compare this data against data of other water bodies in my area.
Yeah. Taking a note of that. Yeah, that's a great functionality. Awesome. Okay. If there are no other questions, Jay, I will pass the baton to you.
All righty, let me take a second and get loaded up here. All right, how's that look?
It's good.
And we're done with the questions on the dashboard, right? Yep, okay. All right, on to part 2, data analysis and interpretation. So first I want to kind of remind you of what we did in, I can't remember which training session number it was, but earlier training on planning and design, just to refresh your memory, where we went through the 18-step program to plan and design a program, and culminating in having a written plan and quality assurance program plan. So keep this in mind. Now I'm going to share 8 steps, it's really 8+ steps with a lot of sub steps on data analysis and interpretation. So it was handy for me, and I hope it's handy for you all to kind of see this laid out in one slide as in kind of outline overall. And I'll walk through the steps. And you'll see, just looking at this slide, things get complicated for mercury, but it's worth the effort to understand what's going on for mercury. Mercury is the bioaccumulative pollutant that's causing the most widespread problems in California, exceeding water quality objectives from the Water Board and advisory tissue levels from OEHA in water bodies all across the state, fresh water, salt water, estuarine. We've got good tools for understanding mercury, so it's good to understand what we've got there. So I'm going to basically share piece by piece the information, the kind of information that we have been including in SWAMP data reports for the bioaccumulation program. The most recent one that's published is from 2019. The 2021 report will be posted soon. But they all have the same format. It's a format that has evolved over the many years that we've been doing this monitoring, and provides the sort of basic important information that's good to record for posterity. And this is a data report, so it's not getting into interpretation that much. It's just the goal of it is just to provide good documentation and presentation of what data was generated in this sampling year. I'm working on an interpretive report for the Bass Lakes monitoring. That's going to have a draft of that in about a month, and so that'll be sent out for review in early January. But so in that kind of report, try to understand, present hypotheses for what might be driving the patterns, the spatial patterns and long-term trends that we see, pulling in other data, doing that sort of thing. But these data reports are really just about presenting the data from each year. Okay, so that was step one, kind of the summary of overall summary of and how we document things. Step two is reviewing raw data tables, and this is important for any project, kind of a fundamental step. Obtaining the data that the labs generate and getting them into a tabulated form that you can present in your data report and that you can use to just see the data that's been generated. It's the kind of data table that Anna was showing being downloaded from the dashboard, but with some a bit of processing to make things easier to look at. All the tables that I'm showing are things that Michael Weaver has written scripts to generate. So Michael's going to go through the process of how you use those scripts to generate the tables that I'm showing. And then these data reports present the data in appendices in these different formats. So this first format is one that I mean, I use all of them a lot, but this is sort of the first one I look at when I'm looking at the data set for a particular round of sampling. It's a cross tab. We call it a cross tab because it's showing multiple pollutants for each sample. So it's handy to see all the data in one table instead of like row by row showing like your mercury results with one value for and then going individual sample and analyte by individual sample and analyte. So this is a better way to sort of see the overall data set. This format is showing mean concentrations for all the samples. So the sample type column, can you guys see my cursor? Okay, good. So the sample type column is telling you what type of mean it is. So one type for mercury is this length adjusted mean. And so it's telling you that. And then for other analytes, we're usually just analyzing composite samples. So selenium, it's a composite sample from this largemouth bass. And then you can just go down. So this table is showing the mercury and selenium data. Something that I find really handy for looking at swamp data sets, for larger data sets, I would imagine that in general, the studies that you guys are doing are not sampling large numbers of water bodies and generating data sets that are very large. So for smaller data sets, it's pretty easy to just eyeball the results that you get. But when your data set's getting larger, using the Excel autofilter feature is really valuable. And basically, if you've got an Excel table like this, you can go to the data menu, and there's you just scroll down and pick the auto filter. You have your cursor, or you have a cell highlighted that's in one of the headers of the table, and then you click that auto filter function, and then it puts a little arrow into the each header cell. You can click on the arrow and filter the data in different ways. You can ask for the maximum concentration. You can ask for values that are greater than a certain level. So like if, something that's when you're trying to compare to water quality objectives, like if you want to compare to the statewide mercury objective, you can say, show all the data that are greater than 0.2 parts per million for mercury. You can show the top 10. You can show the minimum. So, you can show any variation of filtering on the data in that column. So when you've got a bigger data set, it's handy. If you download data from the dashboard and you've got a bigger data table, and you want to kind of see, look at those kind of statistics I was just listing off, then it can be handy for that as well. So now I'm showing a different part of that table that's got some of the organics data. And we don't, in the recent lake monitoring for swamp, we've been very selective in how we do organics, the number of organics analyses that we do, for a couple reasons. One is it's expensive, and our budget has been, we've been constrained with our budgets and trying to make them, stretch them as far as possible. But then also the organics don't as frequently exceed water quality objectives or OEHA thresholds. But this is part of that table that shows a water body or a couple water bodies where we did do organics. One of the standard things we do with organics is the PCBs, DDTs, fluoridanes are classes of contaminants. So there are 209 PCBs, and there are, depending on how many DDTs are in your lab's analyzing, there are 6 or 7 DDT compounds, or potentially more, usually 6 or 7. And what we are interested in is the sum of the PCBs. So we can talk more about this later if people have questions, but when there are non-detects, we set the non-detects to 0. There are other options for dealing with non-detects. You can set them to the detection limit, for example. But if you set the non-detects to the detection limit for 209 compounds, and you add up 209 non-detects, it looks like a big number when it's really not a big number. So standard practice is to set the non-detects for individual organics to 0 when they're non-detects, but then you can focus on the instances where there really is a detection and a solid value to note. So here, Pudding Stone Reservoir, we did detect DDT, 29.5 parts per billion. All these other places we got non-detects. They were all non-detects for all the organics. And that's fairly common that the organics are generally low in lakes. In bays like San Francisco Bay, we do see a lot of PCBs and other organics. But in lakes, they're generally pretty low. Okay, so another one of our appendix tables and data types is for prey fish. Prey fish are something that we've been monitoring in the statewide monitoring. Prey fish are a really good indicator for mercury as well. And there's this a separate water quality objective for prey fish. Prey fish are good for assessing risk to fish-eating wildlife like aquatic birds. They're also handy because in some water bodies, particularly in high elevation water bodies where the predominant larger fish species are trout, a lot of the trout are from hatcheries, and they're not really reflective of the food web in the water body. So in those situations, you can look at prey fish to get a real representation of the degree of mercury contamination of the food web. So we've been doing a lot of prey fish monitoring in recent years, and but it's a different data set. We usually look at mercury and selenium. These are all composite samples, so our design is to get 10 individuals of each species, and then just run them all as a composite. and because they're, that gets enough tissue mass for the analysis, and the fish are of a small size. They're all less than 100 millimeters, so it's a reasonable thing to composite them. You don't have to look at all individual prey fish. So we look at composites of 10 samples. And so this is what we're looking at here, is the composite results for these different species at different locations. I see there's some chat. Anna, just let me know if there's anything I should address in the chat.
Oh, I was just sharing links. You're good.
Oh, okay. Okay, and then another type of data table, another type of data we routinely generate, and that I would recommend if you're looking for mercury in water bodies in lakes and rivers, and in some cases on the coast, is to look at mercury in individual sport fish for the predator species, as a really good indicator of the degree of contamination in the food web. And I'm going to spend some time explaining this, but so it's another type of data table where we show the results for individual fish, the mercury results for individual fish. We only do this for mercury, and in this table, so it's fish by fish, not composites. We measure mercury in each fish. We get the length, which is really important. We use the length to understand the mercury data. I'll go into depth on that. In the state program, we've also been looking at the scales of black bass to estimate age. And the reason we're interested in length and age is that mercury reaches higher concentrations in larger, older fish. It's kind of a melding of these two factors. But as the fish get older and larger, the mercury levels go up. So we've been gathering age data as well in the state program. In practice, I use the length as the key to kind of factoring out the size, age of the fish, as I'll explain in some detail. So these data are sorted by length, and when you sort them by length, you can kind of just by eyeballing see the effect of size on the mercury levels. And this example here is showing reservoir F. It's got relatively low mercury levels, but you can see that the levels are rising in general as you get to the larger fish, and this is a general phenomenon. So that's what the individual data tables look like. When I've got tables like this, I can play around with statistics. And so I'm showing an example here for selenium in sport fish, which is something that we look at composites. We only measure in composites because it doesn't have the same length relationship as mercury, and it's more economical to look at the composites. So I just created a table that had the selenium sport fish data, and then you can, in Excel, just enter the formula to get the count of the sample. So you do insert the formula equals count, and then you put the range of you enter the range of the values that you want to get the count of. So I'm not showing all the entire table here, but there were 109 samples here. Put in the formula for the maximum, for the median, the minimum, and you can also in Excel specify a count of samples with particular characteristics. So here, the count greater than or equal to 1.0. So out of all these 109 samples, only 12 were above 1.0, which is one of the OEHA thresholds that I'll show later. So
Hey Jay, before you
Yeah.
move on, we have a question in the chat. What
Yeah.
about eel or lamprey in terms of the size relationship? Um, Sherry noted they believe the size doesn't correlate as well as age as it does in fish, though folks might find that interesting if the trend is still holding. So do we see that same relationship in eel and lamprey that we
That's
do?
a good question. I don't know the answer because we haven't monitored eel and lamprey.
Okay, great.
Yeah. Um, yeah, I'm curious to know that myself.
This is Sherry. So I'll just I noted I remember when we were looking in the mercury data for eel and lamprey, the eel don't as they get older, they don't always get bigger.
Hmm.
So that was just so yeah, that would be something worth it's a data gap for us to look into, and that's where it comes into so important for tribal training on this because
Yeah.
tribes are looking for different species often, right? So
Yeah.
yeah, stay tuned,
I
I guess, for more info on that one.
Yeah, my guess would be that their concentrations would still go up because the mercury does build up in the muscle tissue over time. That's one of the things that's going on. The other thing that's leading to the higher mercury in the larger fish is that as the fish get larger, they're eating larger prey, which have more mercury. So there's a couple of different things going on. So my guess would be that if the eels are um, just continually eating mercury, taking in mercury through their food and just and getting older, that their levels would go up. Um, in
Yeah.
rockfish, in some species of slow-growing rockfish, but long-lived, we see really high levels of mercury, and that's basically what's going on.
Yeah, so that's part of knowing the how the fish themselves survive in their life cycle to know what's going to be going on with them. So yeah, exactly
Yeah,
like the rockfish, you might have a smaller eel, but it's old and it will have
yeah,
higher levels of mercury. So
yeah.
that's what we were
Interesting.
finding before, but that sounds right with the rockfish as well.
Yeah. Okay, so if I could do sound effects, I would have a sound effect here. Call back to the dashboard presentation. And again, making a plug for the importance of being able to take your data and compare to existing data, either for your water body or nearby water bodies. This would be one of the things I would be doing if I, was going to collect data for a lake in a particular region and have some idea before monitoring of what's going on, and then I'd be eager to get my data and see how it compares. Um, so let's kind of use this real data set and turn it into kind of a hypothetical. Like say um, we went out and monitored Lower Blue Lake, which is the square here, and then in the same year, um, somebody, maybe us, monitored Clear Lake as well. But we got this data point for Lower Blue Lake, which is about 0.4. Um, it's a I'll talk about how we compare to the water quality thresholds, but it's above. It's almost at the no consumption threshold for the sensitive population for OER. Um, Above the water quality objective of 0.2 for the statewide objective. But how does it compare to other water bodies? So we can see that for largemouth bass, if we're comparing the same species, which is a good way to make comparisons, it's pretty similar to what we see in Clear Lake. Um, Blue Lakes was monitored in 2019 and was a little bit lower. Um, Clear Lake has been monitored fairly uh, frequently in the past. So in 2012, we got other values to compare to as well. So in general, this Lower Blue Lake is kind of very, pretty comparable to what we've been seeing in this region. Um, and it's just an example of the value of the dashboard in these graphs, and I think are particularly valuable. I mean, the data tables as well, if you want to like dig into the numbers and maybe do stats, but these graphs are a good first step.
Well, and if I can add to just thinking about prioritizing resources, right? The questions I would ask myself is, okay, maybe the swamp program has monitored these locations, but as we talked about with EL, okay, they've got bass covered. We don't need to spend our resources to analyze bass because we know the swamp program is going to do that. Instead, we're going to monitor eel or plants or something else that has a different maybe sample collection method, more resource intensive, but more targeted to what you're looking for your tribe. And so thinking about all of the data available holistically and thinking about how you want to prioritize your resources with the contextual understanding of the data that already exists. That's how I think about using our swamp data, even for ourselves. Like, okay, we monitored Clear Lake recently in 2023, it looks like. So we might not monitor again for a couple of years. Maybe we'll pick a different location, Blue Lake, because it hasn't been monitored recently. So those are the types of questions as I'm looking at this data that I would ask myself if I were planning to go out monitoring again, given that we're all, we don't have an abundance of resources for, I think, any of us. Anyway.
Yep. And as Sherry said, once you get those data, you can see what species are lower, like bluegill are much lower. And if people are happy eating bluegill, then that's better, better in terms of mercury exposure to focus on species like that. All right, so Anna covered that very well. So now I'm going to go into mercury and this phenomenon of the higher mercury in the larger, older fish, which if you don't pay attention to it, you would get very noisy data and maybe reach the wrong conclusion. So there's a very strong relationship of mercury with length and age. The predators are the most important mercury indicators. When we are trying to track impairment or where there are problems, it's good to look at the predators as a kind of first step. And then, then you can, to understand if there's a big problem in a water body or not, and then you can fill in the gaps for other species and see what are better options for getting lower mercury exposure in a water body. But when we're trying to understand the problem, we focus on the predators. If we ignore this phenomenon, then we could get really noisy data. In the swamp program, we intentionally monitor across a size range. And this is an example data set from Lake Nacimiento, which has relatively high mercury. The legal size limit for black bass is 305 millimeters. So if there wasn't this relationship, or if we were taking a simpler approach, we would maybe just target legal size bass. And the problem with that is when you go out and fish, you never know what you're gonna get. You might get, if you're not intentionally trying to get a fish across a size range, when you go out, you might get fish that are more towards the upper end of what we normally catch, say 400 millimeters. And then in some other water bodies, there might not be as many larger bass there, and you might get fish that are more towards the 300 millimeter end of the range that we normally get. So towards the lower end of the legal size range. So if you're at, and you can kind of see there's a linear relationship here and a pretty steep slope. And if you go with the fish, if you catch fish that are near 300 and you use them to get your mean mercury estimate, you would get a value of about 0.7. And then if you were to get a bunch of fish that were around 400, you would get your estimated average would be about double that, more about 1.4 or 1.5. So it makes a huge difference whether you're looking at fish that are 300 millimeters or 400 millimeters. But we can take advantage of this relationship to remove the noise, or like correct for this slope. As long as we analyze the fish as individuals, we can do a regression analysis and characterize this relationship and come up with an estimate for the middle of the range that we normally where we normally catch black bass, which is 350 millimeters. So the first step is when you've got the individual data is always, many types of data is just doing some graphs to see what you've got. So this is what we show in the data reports for this. This is showing smallmouth bass, where we don't get smallmouth bass at many places. So for smallmouth bass in 2019, we only had one lake, so this was an easy graph to look at. We get largemouth bass at a lot of lakes. So this is what the overall data set looked like. All the data points for individual largemouth bass at all the lakes. And so you can see that there's this relationship where their concentrations generally tend to rise for each lake. The slope of the line for each lake varies. So Sula-Hule Lake had the highest slope, had the highest mercury contamination, these diamonds. And then you can kind of trace the lines for other water bodies, like these pink dots are Millerton Lake, and you can do that for all the water bodies. So the lakes do tend to have this relationship, and we also see this in black bass in rivers and predator species in general. We see this. We also do this for rockfish, some rockfish in the ocean. So this is a general phenomenon. And if you understand this relationship, you can factor out the length effect and get a really robust estimate of contamination. So this was spotted bass. So we had spotted bass at a few lakes, same sort of thing. So what we do and what our scripts do that Michael has developed is to do what I was describing, and I'm going to just show some slides that explain it, break it down into some detail. I've got this menu bar that's blocking part of things. Okay, that's better. So what we want to do is just do a regression on the points for these individual bass points for the water body. So I'm using this reservoir F example. Again, it's not a hot mercury lake, but this works for the lakes with low or high mercury. And so in Excel, just create a little pair of columns with the length data and the associated mercury data. I like to sort them, so again, by length, so you can kind of eyeball them and see what makes sense and what doesn't. And then you highlight the two columns, and under the data analysis menu, well, first you generate a graph. Actually, I got ahead of myself there. You go to the insert menu and insert a scatter plot, and then that'll give you just a basic plot without the regression line on it of mercury versus length. And then if you click on one of the points, it'll highlight all the points, and then you right click and you can say insert a trend line. And then there are options that it asks you if you want to show the equation on the graph and if you want to show the R² value on the graph. So I do that, and that's what I did here. So it puts the line in, inserts the regression line and gives you the equation. So that's a simple way to just get a regression line and the basic info from a regression. This part was derived in a different way, and I stuck this on here later, but I'm going to show you how we get this. But just looking at the regression line, and just eyeballing, you can see at 350 millimeters, the regression line is at 0.1. So basically, that's our estimate of the mean, the length adjusted mean for reservoir F is 0.1. But there's a little more to it to not only get the mean estimate, but to get statistics around the mean, the variance around that mean. So to do that, you go to the data tab and use a regression as part of the data analysis tool pack. And so you click on the regression option, and it asks you if you want to put the results on a separate sheet or on the same sheet. So you tell it where you want the results to go, and then it gives you this output, this regression output. So this is valuable to get the estimate of the variance around the mean. But so it gives you the same statistics. So it gives you that R squared that was shown on that previous graph. And when you just use that option, when you add the trend line to the graph, this also tells you how significant the regression is, which is an important part of our process. We only use the length adjustment when it's a significant regression. So if the value is less than 0.05, then that's significant. That's this F value. And then the other important thing you get from, through Excel, when you're doing this by hand through Excel, is it tells you what the residuals are. So the residuals in graphical terms are just the distance between each of these points and the regression line. So what we're doing with this more thorough regression process is basically length adjusting each of these data points, and the residuals are how you do that. So the residual is the distance from each of these points to the line, and using the residuals, basically we get each of the residuals and then add that to the value at 350. And so that gives us a length adjustment for each of the values. And then with that, so this is what this table is showing. I'm going through this kind of fast because we're behind schedule a little bit, but I'm happy to explain this if anybody's, wants to contact me for more explanation. But so we get the residuals, the distance to the regression line, we add that to the value at 350, and that gives us a set of values, length adjusted values, for each fish. And then you need those individual values to get a standard deviation or a standard error around the mean. So we for working with means, it's good to use the standard error, which is the standard deviation over the square root of n. You can, again, you don't have to take in all the detail right now, but using the standard error and the mean, you can get a 95% confidence interval of each mean, which is a really valuable, simple statistic. And I'll show you the value of that in graphs to come here. So again, please interrupt me if you have any questions along the way. So using this approach, we've developed a really great data set of length adjusted means for black bass throughout California. This is for lakes, but it's also a handy reference for comparing data that we get for rivers, black bass in rivers. I've just been doing that for the Delta, where the Delta RMP has been monitoring largemouth bass throughout the Delta and gotten some comparing to this distribution, we can say are very high values in certain places in the Delta because they're at about 1.5 parts per million for length adjusted bass. So we've got length adjusted values for black bass for 209 lakes now. This graph is just showing the overall distribution. Statewide, 67% of the lakes are above 0.2 part per million, which is the statewide mercury objective. The average is 0.43, and the median is 0.32. But this is a handy reference point for when you get length adjusted bass data for a water body. You can see where it fits in statewide, and whether it's, how contaminated it is relative to other water bodies. And in addition to where it falls relative to the state objective or OEHA thresholds. Okay, I'm going to actually jump ahead to something to illustrate a point about those confidence intervals. So I'll come back to this later, but I just want to connect the dots here with what I was saying about the mean and the confidence intervals. So using that approach with again, that residual output, you can get estimates of 95% confidence intervals. The mean plus or minus 2 times the standard error gives you a 95% confidence interval. So that's really handy when you want to compare values over time or over space. So that's what's showing on this graph. Or I'll focus on Coyote Lake because the title's not being blocked for me. So Coyote Lake, we we monitored in 2008, then 2016 and 2017, and you can look at these, these 95% confidence intervals are a good guide to whether there's really significant variation over time. The 95% confidence intervals for 2016 and 17 don't overlap, so there did seem to be an increase. That's it's not strongly significant because the confidence intervals almost overlap, but there was a difference from 2016 to 17, but neither of them were very different from 2008 because the confidence intervals overlap. So long term, we're not seeing much of a trend over time here, and you can use this confidence interval approach to get at that information. Okay, now I'm going to go through thresholds and fairly quickly. And there's a kind of assortment of thresholds to compare to. And I'm just gonna, the tribes may have your own thresholds that you like to compare to, but I'll go through what the state uses and what OEHA uses. So for predator fish, for water quality objective comparisons, there's a statewide objective that has been established, or objectives really. So for sport fish, there's an objective of 0.2 parts per million. I'm showing the document that this came from, and again, you've got, you'll be able to find the information. Anna's got links to this earlier in the slide deck. But for sport fish, I've been mentioning this 0.2 part per million objective for predator fish. So predators are trophic level 4. There are tables that tell you what fish are trophic level 4. It tells you what size to use. And for black bass to focus on legal size. So if you're interested in strictly comparing to this objective, then you use legal size fish. So this is different from the length adjusted average. You would just use a simple average of fish that are 305, between this 305 and 500 millimeters, and compare it to 0.2. There's a tribal subsistence objective. And if you want to do a rigorous comparison to this objective, it's 0.04 parts per million, but you need the trophic level 4 fish and trophic level 3 fish. So in your design, if you really want to evaluate this, then you would need to not only sample the black bass, but also some trophic level 3 fish. And I've got a table coming up that shows what species here fall into each category. So for freshwater, trophic level 4 fish are the black bass, pike minnow, channel catfish, etc. Trophic level 3 fish, so they're lower trophic level, lower in the food chain, things like carp, bullhead, bluegill. So if you really want to compare to this state objective, to the tribal objective, you would need to monitor a mix of trophic level 4 and trophic level 3. And there's similar breakdown for marine estuarine fish. Okay, that's the state water board objectives, and then there's the OEHA thresholds, and there's advisory tissue levels is what I think is what OEHA uses when they develop advisories. I think it's the one of arguably the most important thing to compare to. And so OEHA, when they do their assessment, they use a slightly different approach. They don't do the length adjustment. They just use an average of legal size fish. So any legal size fish, anything above, so for black bass, anything above 305 millimeters, and you compare the average to the ATL. So as an example, OEHA just published advice for Modesto Reservoir based on swamp data, and there's a report that goes with each advisory, and so I pulled this from their report, and they show a summary of the data for Modesto Reservoir. So for black bass species in general, they got a mean, just a simple mean of legal size fish of 253 parts per billion. For black bass. For threadfin shad, for example, there was also a threadfin shad sample. They got a mean of 22 parts per billion. It was only one sample, so it was one of our prey fish samples. So they summarize the data in these tables, and then compare those values to their advisory tissue thresholds. And Wes Smith is going to go over these values in detail, but this is the table that summarizes all of the advisory tissue levels for all the contaminants for mercury for the sensitive population. That black bass value fell in this 1 serving per week category, so it was 253 parts per billion, so it falls within this range. The threadfin shad, so this is 1 serving per week. Threadfin shad was at 22 parts per billion, which is in this less than or equal to 31 parts per billion, which is 7. It's safe to eat 7 servings per week at that level. So that's how OEHA is using these thresholds and generates the advice. So this is the advisory poster for Modesto Reservoir. Black bass was 1 serving per week for the sensitive population. Threadfin shad, 7 servings per week. For prey fish, the state also has a water quality objective. So going back to the same document, and the objective for prey fish to protect wildlife is 0.05 parts per million. There's also an objective for areas where there are least terms, but you can read that on your own if you want, if that applies to you. But the more general objective is 0.05 that applies across all water bodies. This is for fish. You have to pay attention to, the details. So this is for any species between 50 to 150 millimeters during the breeding season, because they're protecting breeding birds, and it tells you what the breeding season is. So we collect our swamp data. Our prey fish are less than 100 millimeters, but they fall within this range. And so showing from our data report, a graph by species to comparing to this 0.05 parts per million. It's handy when you've got a variety of species to show the graph this way, and see how the species vary. And then you can also show by water body. This was from the 2017 report, I think, where we sampled a bunch of water bodies, and you can, this pink line is the 0.05 threshold, and these are averages across we usually sample 3 different species at each water body for swamp. So this is the average by water body. But again, comparing to this 0.05 threshold for prey fish. For other contaminants, they've got their own thresholds. Other key contaminants for bioaccumulation are PCBs. PCBs are second to mercury in terms of driving advisories and concern across the state. DDTs and selenium generally aren't driving advisories, so lower level of concern. PFAS is driving a lot of concern, but California doesn't have thresholds yet, so I'll talk more about that. For PCBs and DDTs, the state, well, you can compare to advisory tissue levels, and the state uses fish contaminant goals, which are another set of thresholds from a WIHA. And for PFAS, again, we don't have California thresholds yet, but we've got a lot of data for San Francisco Bay. And when we present those data, we compare to thresholds that have been established by the state of Massachusetts. Other states have established thresholds, and so we use that as a frame of reference. It's not an official threshold for California, but it gives you some idea of what's going on in the how problematic the levels are. So for PCBs, the advisory tissue levels, kind of ones to note. When you're over 120 parts per billion, that's the no consumption range. And we do see levels like this in San Francisco Bay, San Diego Bay, not very infrequently in fresh water. At the low end, when you're below 9 parts per billion for PCBs, you're in the high consumption safe range. So DDT, the high end is 2100 for no consumption. Below 220 is pretty safe for consumption at 7 meals per week. We don't often, basically never see DDT concentrations at this high. So even above 220 is unusual, and except for maybe a place like Lauritzen Channel in San Francisco Bay, where there was a DDT manufacturer that caused contamination. We don't see levels that high. Selenium, the upper end's over 15,000 parts per billion. At the lower end, when you're below 1,000, it's pretty safe. We do see sometimes, and I showed in that table, I had that statistic counting the number over 1 part per million, which is 1,000 parts per billion. There were 12 samples that were out of 109 that were above this level. This is a low level of concern, but that we do see some values that are of some concern for selenium at a high consumption rate. And then there are fish contaminant goals, which is something that the Water Board uses in their integrated report for organics. I'm not going to go into the details here, but they're different from the advisory tissue levels in that they don't take into account the health benefits of consuming fish. So they're lower, more conservative values. So for PCBs, the FCG is 3.6. So this is another threshold. So the ATL for 7 meals per week was 9. So that was kind of the low end for ATLs. For the FCG is 3.6. So this is a threshold that the state uses for listing water bodies for PCBs. So it's noteworthy, but more conservative than the ATL. And then DDT again is lower than the ATL. Selenium, the selenium FCG is higher than the low ATL. Okay, so that was a quick run through of thresholds that are available. I'm nearing the end of my presentation. We can take our break. But going back to step 6 is once you've gone through all that, you've compared to your thresholds, and you want to look at whether there are trends over time. If you've got data from prior years, then you can do this. And so this is how we do this. We've got our best data for mercury in general. So, and we're over in recent years, we've started to get to a point where we have time series of data, and we've revisited water bodies. Like Collins Lake, I couldn't see the title, but I moved the thing, so now I can see it. So Collins Lake, we sampled in 2017 and 2008, and these confidence intervals are not overlapping, so not much change. In the up through around 2017, when we were revisiting lakes, we weren't seeing much change over time. I've been looking at the more recent data, and things do seem to be showing more signs of change over time. So stay tuned for the interpretive report that I talked about, where I'll be summarizing that. But in general, we see remarkable consistency and within water bodies and over time. As you can see here for Collins Lake, Coyote Lake we talked about before. And so this is a kind of a medium contaminated lake. Coyote Lake's getting higher, not above 1 part per million, but around 0.8. And then also for clean lakes, relatively clean lakes like Ferguson Lake, the low values are consistent over time. So there's 2 different flavors of significance. There's significance in terms of comparison to the whatever thresholds you want to use. So relative to 0.2 here, you can compare these points relative to that threshold, and they're not changing for Collins Lake, Coyote Lake. And then you can compare the points to each other to see if there's a trend over time. So that's a different kind of statistical significance that's you can look for. Ferguson Lake's also staying below the 0.2 part per million threshold over time. So these are 2 different things two different ways you can interpret your data, whether comparing to objectives or comparing to other time points. Another thing you can do is compare spatially, which I'm just rearranging those same lakes to do the spatial comparison that I was talking about, where you can see Collins Lake And we can compare these confidence intervals of these means to see that Collins Lake is significantly different from lower than Coyote Lake, because these confidence intervals for Collins Lake are below the ones for Coyote Lake. And then Ferguson Lake is the lowest of them all, lower than, significantly lower than Collins Lake, and even, way lower than Coyote Lake. So these means and confidence intervals are handy for doing these comparisons. Okay, and then step 8 is reporting. So you use all these scripts, and it's really important to generate a good data report, even if it's a small data set, and then uploading to the database is another important step. So again, this example data report, the contents of a data report, for a small study, you may not need all of these elements, but like maybe not, well, I don't know. Executive summary is good for any project, like a short summary at the beginning of the document of the take-home messages. I think a little bit of each of these is good for any study. So an introduction, the goals of the study, documenting your methods is important. And then, of course, the results. And again, data report doesn't really get into discussion or interpretation much, but if you are doing interpretation, then you would include a discussion. And then these graphs that that I've been showing you examples of, and Michael's gonna tell you how to generate, how to use the scripts for them and the tables. An important thing to include in a data report, I like to attach them to the data reports, is a cruise report for documenting the sample collection. So Appendix 1 is a cruise report. I'm going to show you what that looks like. And then these tables that I've been showing, different tabulations of the data for the sport fish, prey fish, and individual fish. So cruise reports are really valuable if you're, I think, for any monitoring effort, and especially if you're going to be doing something where you go back in the future and sample the same water body. Moss Landing has been doing the sampling for the state for the bioaccumulation program since it began, and they write really good cruise reports. These are all available on the Safety Work Group website, and there's a link here. They provide a summary kind of overall of the sampling effort and what the design was, the targets, etc. But what I really want to show you is what they report for each water body where they sample. And it's easy these days with Google Earth to show exactly where samples were collected. So that's what they do. They give the latitude and longitude. When they do their sampling, it's with usually with an e-boat, an electrofisher boat. So it shows the path they took when they did their fishing on the e-boat. If you're sampling with hook and line, you would just show the points where you're sampling, wherever they might be. Give you the collection date, who was sampling, and then a breakdown of the fish that were caught. And then it's important, it's of course very handy to kind of see, document what fish were caught. They measure the fish in the field to get the lengths. That's helpful for tracking the fish. And then this comment field is important, where they provide information about access, what kind of permits you need. It's also a place where you can say if there are difficulties finding a target species, or if there were other species observed that you might want to sample in the future, you can record it here. So this is really important for implementing a monitoring program over time. All right, that's the end of my slides. You guys are
Awesome.
probably ready for a break.
Yeah, we're past our target time, but we have a lot of flexibility in the rest of our schedule. So why don't we take a 15-minute, 16-minute break and come back at 11? Does that work for folks? Give me a thumbs up or reaction, or if you just don't want to break it all, you can give me a little. Okay, cool. We'll see you all back here at 11. Have a good break, y'all. All right, welcome back from your break, y'all. Hopefully you took one. If you have questions, feel free to reach out to Jay or myself after the recording today or the class today. And with that, we'll pass over to Michael, who'll talk us through scripts.
Great. So I'm just going to go through the scripts for data analysis that are basically just kind of automating the processes that Jay described for analyzing a data set for um, Mercury. And basically the steps that we're going to follow to use these scripts. First, we're going to download a data set from the CEDEN query tool. And that's going to give us a nice TSV file. Then we're going to download the scripts from this State Water Board's GitHub repository, and install the script package in R. And first, before you do that, you got to make sure you have R and RStudio installed. Um, so then there's a little extra setup before you can get started. You need to make the folder that you have the download file in your working directory, and you need to load the package that you've installed. You can do that with R's library function, where you just you run the library function on the name of the package. And once you do that, you can start running the different functions from the package. The first thing you do would be to run the data summary tables to generate all the appendix tables that Jay talked about, and then you go through and run the other functions for the mercury analysis for predator and preyfish. And I'm gonna walk you through those real quick now. Oh, well, first, actually, I'm gonna walk you through downloading data from CEDEN. So I think it was mentioned that getting data from CEDEN can be a little tricky. They did kind of without much fanfare update their data download portal, which is called their advanced query tool. So it's a little easier now. There's this part on the left is the query filters that you can use to select your data set. And here you see I'm just downloading a bog data set from a couple years ago. And sorry, once you select your data set, you'll go to a table view to see the data set in a table, and then you can hit this export to TSV button, and that will give you a data download. So there's a lot of filters, which makes it seem a little tricky, but the big things are make sure you have the right category selected. If you can't see in the little screenshot that I have here, I have tissue selected, and then I have a project name, and that was basically it to get the data set. Oh, great. And I'm just going to talk quickly about the basically the tools we're using for the data analysis environment. These are all kind of open source tools, so they're free for everyone. R is a program that's pretty widely used for data analysis, and RStudio is a platform to run that has some extra tools to make everything simpler. And basically, you're going to install those and then download the package from the GitHub repository that the water board has set up. And a pretty easy way to do this that I'd recommend is there's a couple packages that you can install first. Either the DevTools package or the remotes package both have a function to install from a GitHub repository. So you can just, you install one of those, you can just run a function where you put Cal Waterboard's waterboard data center / the name of the repository, and it'll install the package for you in R. Great, and this is just kind of a view of what it'll look like. Basically, once you have the package installed, you can run the functions from the R console. This is the summary tables function that generates all of those appendix tables, and basically the only parameter you got to pass to it is the name of your data file, which should probably be in quotes, but just pretend. And once you do that, it'll output a spreadsheet with summary tabs for each of these tables that Jay mentioned earlier. The appendix with the compositor means of individual fish, where the means of individuals are calculated for mercury and are length adjusted if they're able to be, if they meet the criteria, and composite results for prey fish at each location, and then mercury results for individual sport fish. And I don't know if Jay talked about this, but it'll also generate some summary information with the counts and min, max, and median length information in separate tables for sport and prey fish. And those will all be in one, generated in one Excel spreadsheet if you run that function.
Michael, you're right. I didn't mention those, but they are handy tables. Good things to include in the data report.
Right. Yeah. And this another function is a length adjusted average script. This is actually wrapped up in those summary tables, but running this function gives you the ability to generate them on their own. It also will give you an output with showing all the calculations that go into generating the averages, which is helpful to see. And basically all this does is it takes a subset of the mercury results in your data set for individual fish, meaning fish that aren't composites of multiple fish, and it calculates the length adjusted means on a grouping of project station, location, and species. And then it checks that you can actually that the length adjusted mean is good to use. Basically, as I think Jay was talking earlier, it has to have, the regression has to be significant, and it has to have a certain number of fish included as well to be useful. And if it doesn't, we substitute that with for largemouth bass, smallmouth bass, and spotted bass for a mean of the results, where the average total length is between 305 millimeters and 395 millimeters, and for other species, it just takes a simple mean of the results. And those will be which of those is used will be in the output and the result type field, as Jay showed you. And this is how we generate these species bar plots for mercury concentrations, and comparing to different thresholds, which you can see are represented by those lines there. And basically, this is just another simple function that you run, except for this one has a couple parameters. You'll input the file name, and also whether you want to see crayfish or sport fish, and those would be output in different plots based on what you select. And pretty similarly, there these mercury versus length scatter plots that Jay talked about. There's a function to generate those. It just looks at you give it the input file name and what species you want to see it for, and out comes the plot. Yeah, that was it. Those are our scripts.
Yeah, short and sweet. I want to do some full disclosure here. One, Michael and I are still working on getting the GitHub repository populated. So we're packaging the package, as it were. But we're going to work together on that after this training. And when that's ready to go, I'll send an email announcement out to folks that have registered or attended. And I'll also maybe add a link to the website just for easy access. And yeah, R is great if you're thinking about trying to automate your process. If you're just doing like a one-time analysis, it might be easier to just, pull things and work in Excel, and that's totally fine. Folks like Jay and Michael and I and others, we like to use R because we're doing the same sort of things over and over and over and over. So being able to automate that using scripts like Michael just walked through is really helpful. But maybe that's not your jam, and that's totally fine. I also added links to an R training resource that was actually developed for water boards employees. There's an introductory section and an advanced section. It's called R Forwards, R for water data science or something like that. And it walks through like how to get everything set up and what R is and R Studio, and a lot of the terms that Michael said that are pretty common vernacular when you're a coder. But if you've never coded before, like what the heck is a package and GitHub and like that just probably sounded like gobbledygook for a lot of folks. But that training series walks through those resources, and it's online and it's free, so anyone can access it.
And I just also wanted to mention that the package itself in the GitHub repository will have a README file with instructions for how to run everything. And it'll also have all those different functions documented, so you can know what they're doing and how you need to use them.
Yeah, this is great. Any questions for Michael before we wrap up? Or for Jay, if you've been marinating, you're like, oh yeah, I have an analysis question. Opening the floor.
Or if anybody's willing to talk about what monitoring they've got going on, I'd be interested in hearing that.
Okay.
I can say one thing. I know that as we move into this is bioaccumulation related to fish tissue, but we do need some support on plants, and we also need some support on how some of the underpinnings of creation of water quality objectives were arrived at. So, like for mercury, we can go through the ASWEBE and we remember the process of how those numbers came about. But for some of these other toxins, especially the ones that have older water quality objectives, it would be really helpful to know where these came from. So that might be a to-do list for us in the future.
Yeah. Thanks, Sherry.
Yeah.
Um,
I'm gonna stop sharing.
yeah, go for it. I'll reshare and take us home. We might be stopping early today, y'all.
Unless anyone has any questions, no questions are dumb questions. We could, since we're not, we could stop recording if you're not comfortable with your questions being out there for the planet. Maybe
Yes.
that would make things easier. But otherwise, we could wrap it up and say thank you and then stick around for a minute to answer any other offline questions.
Yeah,
Sure.
I'd be happy to do that. Let us walk through just some closing things. I have one more poll. And a reminder, there was a question, can we get these links in a follow-up email? You betcha. It's coming at you as soon as I can put them all together and get the recording link available. I'm hoping by the end of today, but definitely tomorrow morning at the latest. You all will be receiving emails in your inbox with all the goodies. In fact, I'm gonna try and get the recording available on YouTube today, but then I'm gonna post it on our website. That takes a couple days, but that should be up by the end of the week. So if you are not sure and go to the website and it's not there yet, just give it another day or two and it'll show up. All the recordings and slides from the last trainings are available on our webpage. So I mentioned in the chat, we referenced certain things back in September about integrated report, or back in February when we talked about sampling design. All of that, links to that content is on our webpage and it's open to anyone. Next week on Tuesday, our OEHA partners, Wes Smith and Lauren Chumney, are going to be talking about their process and breaking down equations on how OEHA creates fish advisories, as well as covering some high-level material. And they are, buttoning up their presentation, but wanted to see if you're planning on joining, what information you're interested them in covering and or spending more time on. So I'm going to launch a poll, and this is a select all that apply. So if any of these make your heart feel good things, then check the box. And I'll be sharing these the poll responses with OEHA so they can get a sense of how they want to adjust their slides. So basically, are you looking for a general overview of OEHA and fish advisories in general? A refresher on how they use and collect data for their specific risk assessment analyses, and how they evaluate the data, how they decide what priorities are in terms of which advisories are developed first, and how advisory tissue levels are developed. So that is specific to the PFAS conversation. Jay mentioned that California doesn't have thresholds yet. OEHA is in the process of developing advisory tissue levels, and they're going to talk about what they're thinking about to do that. And then anything else, if you hit something else, please share in the chat what it is so I can pass it along. Okay, we've got 10 out of 13. And I have a feeling Michael, Jay, and I are the 3 that aren't participating. But I'll give it another couple seconds just in case. Okay, great. I'm going to end the poll and then share the results. And what I'm seeing here is we want a little bit of everything, which is about what I thought the results were going to be, but it's helpful to know that folks are interested in understanding how OEHA evaluates data, how ATLs are developed. So I will pass this along. Actually, I'm going to take a screenshot right now. Hold on. Bear with me. From my phone, low tech, and pass that on to OEHA. Okay, thank you for doing that. And thank you for being here. Starting at 9 a.m. on a Monday is rough, and we appreciate you jumping on, spending this time with us. And if you have questions about anything that we covered today, Jay and I are available to you. Our emails are on the slide, and I think that's it. Oh, there's links to all of the slides in the recording. If you haven't yet registered for the OEHA training next Tuesday, definitely check out the registration link. And the links and everything that will be shared, that were shared during the chat today, I'm going to put on this slide. So when you get the slides, this will be populated and ready to go. But with that, I'm gonna stop the recording. If folks want to hang on and ask questions, you're more than welcome to do so. But for those online, thanks for watching the recording. Thanks for hanging with us. And we'll see you hopefully next week.